recall that for a function f of xy, the value df, which is partial f partial x dx plus partial f partial y dy, is called the total differential. Now it is known that this total differential is identically equal to 0 in certain regions of the xy plane. Then the function must be constant in that region. So this will lead us to our next type of differential equation. So a differential equation, m of x y dx plus n of x y dy, is an exact differential in a region R of the xy plane if it corresponds to the differential for some function f of xy defined in the region R. The equation m of xy dx plus n of xy dy equals 0 is said to be an exact equation if the expression on the left is an exact differential. Now this is all well and good, but we need a way to test whether a differential equation is exact or not. And this next theorem gives us a way to do that. So let m of x, y, and n of xy be continuous. And have continuous first partial derivatives. In a rectangular region R that is defined AB crossed with CD. Then m of x, y dx plus n of x, y dy is an exact differential if and only if partial m partial y is equal to partial n partial x. So this is our test. We are going to prove only the necessity statement. That is, we will prove that if this is an exact differential, then this equality holds. So let us assume that m and n have continuous first partial derivatives for all points x, y. We make this assumption for simplicity. Also, just for the ease of writing, it is understood that m and n are functions of x, y. I just will not be constantly writing the x, y. So now, if m dx plus n dy is exact, then there must exist some function f such that for all x in a region R, m dx plus n dy is equal to partial f partial x dx plus partial f partial y dy. Right? This is from the definition that we just saw. So we must have m is equal to partial f partial x, and n must be equal to partial f partial y. Furthermore, partial m partial y would have to equal partial partial y of partial f partial x. So this is the second partial derivative of f, first with respect to x, then with respect to y. Remember, when looking at mixed partials like this, the order of the differentiation is read right to left instead of left to right. But the order actually doesn't matter, remember? I believe that was called Fubini's theorem. No, I'm sorry, Fubini's theorem is for multiple integration. In either case, this order does not matter. So I can just as easily write this in this form, which is, of course, partial partial x of partial f partial y. But that is partial n partial x, right? Because this term here is our n. This proves the necessity part. We've shown now that partial m partial y is equal to partial n partial x. And so the proof is complete. The sufficiency part, so the other direction, would involve showing that there exists a function f for which we have this condition whenever this equality is satisfied. Again, we will not be doing that here. Let's now look at testing whether differential equations are exact. So let's first look at the differential equation. X squared plus y dx plus x minus sine of y dy is equal to 0. So here, our function m is x squared plus y, and our function n is x minus sine of y. So we want partial m partial y first. Well, this is just 1. Now we want partial n partial x. Well, once again, that's just 1. They're equal, so this is exact. Now consider the equation x squared y dx plus x cubed over 3 plus 4y squared plus 1 dy is equal to 0. In this case, our function m is x squared times y, and our function n is x cubed over 3 plus 4y squared plus 1. So partial m partial y is x squared. Partial n partial x is x squared. Therefore, this equation is also exact. Finally, let's look at the equation. X plus y dx minus x minus y dy is equal to 0. So m is x plus y, n is negative x plus y. Remember, it has to be m plus n. So we just have to distribute this negative through to make it a plus n. So partial m partial y is 1. Partial n partial x is negative 1. These are not the same. So this equation is not exact. We now look at how to solve a differential equation that is exact. So we have an equation, m dx plus n dy equals 0. And we also have that partial m partial y is equal to partial n partial x. That is, this is exact. Well, there must exist some function f such that partial f partial x is equal to m. Now, we find f by integrating with respect to x. So this implies that f is equal to the antiderivative of m with respect to x. Now, when we get this the simplest antiderivative is going to be a constant function that has to be added, so we add it here, plus some function g of y, where g of y is just some arbitrary function. Now we take this and differentiate it with respect to y. So partial f partial y is equal to partial y of this integral plus the derivative of g of y. Since g of y is a single variate function, we can simply write this as g prime of y. But partial f partial y has to equal the function n. If we solve for g prime, we find that g prime of y is equal to partial y of the integral m dx minus, I wrote that backwards. It's n minus partial y integral of m dx. We need to find what this arbitrary function g of y is. We can do this now by integrating both sides of this equation with respect to y. So this will give us that g of y is equal to the integral of n with respect to y now simply minus the integral of partial y of the integral m dx. And of course, this is with respect to y. The implicit solution then. So replace first this g of y into here. And we get that f is equal to the integral of m dx plus the integral of n dy minus the integral partial y of the integral of m dx with respect to y. So the implicit solution to now the exact equation up here has form f of xy is equal to some constant. But remember, this is our f of xy. Now, in this method, you could also easily switch the orders of m and n. That is to say, instead of starting with partial f partial x equals m, you could start with partial f partial y equals n, and then follow a very similar procedure to get a very similar f. In actual practice, it doesn't matter the order in which you do it, you're going to find that f is always the same. The difference is, in the general case, this will look different, but it'll actually be the same. So let's go ahead and solve the differential equation x squared plus y dx plus x minus sine of y dy is equal to 0. So the first thing we need to do is check that this is an exact form. So partial m partial y is 1. Partial n partial x is also 1. So this is exact. So partial f partial x has to equal m, which is x squared plus y. So this implies that f is equal to the integral of x squared plus y with respect to x. So this is x cubed over 3 plus xy plus some arbitrary function of y. Now this means that partial f partial y would have to be x plus g prime of y. But this has to equal n, which is x minus sine of y. So this means that g prime of y is equal to negative sine of y, which means that g of y is the integral of negative sine of y dy, which is cosine of y. Therefore, our f is x cubed over 3 plus xy plus cosine of y. Now technically, there should be a constant, right? However, I'm about to show you that we don't need this constant. The solution would be x cubed over 3 plus xy plus cosine of y plus that constant is now equal to a constant. Let's call this constant c prime. Well, wouldn't you just subtract this constant from both sides? And a constant minus a constant is still constant. So this is why you actually do not need to add this plus c. So I'm going to rewrite this as x cubed over 3 plus xy plus cosine of y is equal to some constant, and there's our solution. Now let's consider the differential equation e to the 2y minus y times cosine of xy dx plus 2x e to the 2y minus x cosine of xy plus 2y dy is equal to 0. So partial m partial y is equal to 2e to the 2y plus, now we have a product rule. So negative y times negative sine of x times y times x plus cosine of x times y times negative 1. So what we're left with is 2e to the 2y plus xy sine of xy minus cosine of xy. Partial n partial x, we get 2e to the 2y plus, now again we have a product rule, so we get negative x times negative sine of xy times y plus cosine of xy times negative 1. And so this simplifies to 2e to the 2y plus xy sine of xy minus cosine of xy. Those two are the same, so this is exact. So partial f partial x has to equal e to the 2y minus y cosine of x times y. This means that f is the integral of e to the 2y minus y cosine x times y with respect to x. This equals x times e to the 2y minus, so I have to take a look at here, this is going to be a u sub, So the derivative of x times y is y with respect to x. So we have a y here. So this is essentially now the integral of negative cosine u du, which is negative sine of u. So this is minus sine of x times y plus a function of y. Integrate this now with respect to y. I'm sorry, differentiate this now with respect to y. 2x e to the 2y minus x cosine of xy plus g prime of y. Now this has to equal n. So this has to equal 2x e to the 2y minus x cosine of xy plus 2y. Which means that g prime of y is 2y. And so g of y is the antiderivative of 2y dy, which is simply y squared. So our function f, 2x e to the 2y minus x cosine of xy plus, I'm sorry, I was reading off the wrong line. F is x e to the 2y minus sine of xy plus y squared. Remember we saw in the last example, I don't need a constant. So our solution, x e to the 2y minus sine of xy plus y squared is equal to some constant. Let's now look at initial value problem. We will have dy dx is equal to xy squared minus cosine of x times sine of x all over y times 1 minus x squared, with the condition that y of 0 is equal to 2. Now let's take this equation and rewrite it. So what we're going to do is we're going to multiply both sides by the y times 1 minus x squared, and also multiply both sides by this dx. So we get y times 1 minus x squared dy is equal to xy squared minus cosine of x sine of x dx, which can be rewritten xy squared minus cosine x sine x dx minus y times 1 minus x squared dy is equal to 0. So partial m partial y, 2xy, partial n partial x is also 2xy. Good, this is exact. Now in the previous two examples, I started with partial f partial x. However, if we look now, what's easier to do? Integrating this function with respect to x, or integrate this function with respect to y? Well, the answer is integrating this with respect to y. So that's where I'm going to start. So for this example, I'm going to go partial f partial y is equal to negative y times 1 minus x squared. This means that f is the integral of negative y times 1 minus x squared with respect to y, which is negative y squared over 2 times 1 minus x squared plus some function of x. So partial f partial x is positive xy squared plus g prime of x. But this has to equal xy squared minus cosine x sine x. Which means that g prime of x is equal to sine of x times cosine of x. Negative cosine x sine x. I'm going to use a trig identity. So this is negative 1/2 sine of 2x. This means that g of x is the integral of negative 1/2 sine of 2x which is 1/4 cosine of 2x. So f is equal to negative y squared over 2 times 1 minus x squared plus 1/4 cosine of 2x. And our solution would be 1/4 cosine of 2x minus y squared over 2 times 1 minus x squared is equal to some constant. Or we could also write 1/2 cosine 2x minus y squared times 1 minus x squared is equal to a constant. Notice all I did was I multiplied everything by 2. And of course, 2 times a constant is still a constant. So that is our general solution. We now have to apply the condition y of 0 is equal to 2. So again, remember, y of 0 equals 2 is the same thing as whenever x equals 0, y equals 2. So in here, we plug in 0 for x, 2 for y, and that'll tell us what c is. So 1/2 cosine of 0 minus 4 times 1 minus 0. Cosine of 0 is 1, so we get 1/2 minus 4, which is negative 3/2. Not 3/2, sorry. It's negative 3.5, which is negative 7/2. So our particular solution is thus 1/2 cosine 2x minus y squared times 1 minus x squared is equal to negative 7/2. That concludes this lesson. I hope you learned something, and we will see you in the next one.